We must solve the hydrogen problem. China is making solar panels right now for sale in other countries for 8 cents a watt. You take an 8-penny module, DC directly on the dirt, and you put it into a very inexpensive electrolyzer, and you make hydrogen. You make a hydrocarbon that's transportable to the rest of the world. China's using their hydro to get control over solar, and solar is now the cheapest, period. Convert that into hydrogen. You have a very serious strategic problem if you don't start making the stuff in this country.
Jim Tyler has been on the vanguard, on the forefront of how we build solar projects, how we think about semiconductor as a transformative technology. And I finally have a chance to do as many of my friends have, journey to Tempe, Arizona, and have him tempt me with the idea and see if he can convince me and you that this new way is the way. Are we really at the point where we can lay solar panels flat on the ground? And if we suppose that eventually solar panels and solar panel technology, the energy that comes off of it, is essentially free, what then? What does it free us to do? We're going to talk about that and so much more today on Suncast. Thank you for tuning in. Let's get ready to tune up your skills, Solar Warrior, as we tune into this episode with Jim Tyler of Erthos. Could you put me in the place and time where you began to brainstorm what would we do if energy were free, if solar panels were free? When we first got in the industry, we were anything but. We were paying north of $5 a watt. Help me understand sort of the thinking that you began to go through and where you were at in your career evolution as solar panels dropped to such a precipitously low price.
From the outset, when I was at OptiSolar, built the first plants in Sarnia in Canada, 2008, the stock market crash. OptiSolar gets bought by First Solar, move over to First Solar, help build that team to, its pinnacle in about 2012 or so. I recall at one point we had 21 parallel projects under construction, 10,000 people, something like that in the field. It was absolutely crazy. Left First Solar, founded Depcom with a whole series of people from First Solar, and went along through the process of watching, going at First Solar doing thin film modules on fixed tilt racks to crystalline silicon modules on trackers, bifacial crystalline silicon modules on trackers, ultimately to the technology that it is today. Just being involved in all those technologies, I had done just about everything you could do within the industry, and essentially retired. I had been all over the world, Australia, Chile, South Africa. We built the first plant in Dubai. Just an amazing process, right? A lot of different experiences. The idea of the solar panel being free, that actually is what hit me. I had left the industry completely. Was out for more than a year, and was just riding my bike, and it just dawned on me, and it became really obvious right away. As soon as that idea hit my head, it was like, well, you'd put them on the ground. You'd get rid of all the rack and the steel and the extraneous materials. You'd put them on the ground. And I got home that day, and I was really excited about the mathematics of it, the calculus of it. When I was at First Solar, we developed all the tools and the calculus around that at First Solar. So I essentially took some of the publicly available tools from NREL and modeled, how it would be done. And there is a very specific answer of the tipping point that I call, what's the price of the module where it makes more sense to put it on the ground than it does to make it put it up in the air, right, on a rack. And this is, again, back in 2018 timeframe, 2019. And that number came out to about 48 cents a watt. And I had bought a module in 2018 for a project at 27 cents a watt. It was like, what the heck? That just, I fell over. I couldn't believe it.
We're already over optimizing.
We were already over the number, and I'm like, okay, well, usually the way the industry works, it's really smart. The whole industry is very, very smart. You went from dual axis trackers to fixed tilt facing south to single axis trackers, sometimes tilted single axis trackers, now to bifacial. All those sequential moves were all based around the price of the module changing and the efficiency of that module changing. And so when we ran the model and figured it out, decided, okay, go from zero and backwards. And where was that tipping point? It was about that 48 cents. So I was like, man, somebody had to do this somewhere in the world. Well, I started searching, couldn't find anything. And then I went and hired a very good attorney in San Francisco to begin the process of looking for just public documents, communications, patents, prior art, the whole thing. And they couldn't find anything. And
to be clear, anything suggesting that someone was laying panels flat on the ground, right?
The right way to think about it is orienting a panel to the earth rather than orienting a panel to the sun. That's really the difference.
Wow.
So, and rooftops, putting a panel on a roof, well, that's wherever the shape of the roof is.
Right.
But putting a panel oriented to the earth, the difference is that versus putting a panel oriented to the sun because you put it on a rack and either faced it south or you tilted it east to west.
Yep.
So that's the fundamental, that's the baseline idea of the patents. Many people have conceived of putting stuff on the dirt, but they just never did it.
Yeah.
So immediately submitted for patents, just straight away, and fast-tracked the first one, the important one, the critical important one, and received that patent after about 11 months. Mm-hmm. And but it wasn't just, oh, you've got a patented idea, right? That's just an idea. You got to move past that and into, how do you actually do it?
And what was that first IP? What was that first patent?
It's fundamentally the idea of orienting a panel to the earth rather than the sun.
Got it.
Placing it flat on the dirt, not on some membrane between the dirt and the panel or some object that sits on it.
Right.
Any of it. It's just literally on the dirt.
Right. So there are, to be clear, there are racking companies. I've seen projects. We had one at Trina that was literally mounted on the ground, but with traditional roof racking, right? It's still aluminum or steel.
That exists.
And also, I think at least one project took the old Powerlight panels with their foam, their polystyrene base and put them flat on the ground. I think at an airport, but no one had actually
stuck the panel on the dirt.
Frame on the
frame on the dirt.
This is a carpet of solar.
Mm-hmm. So it's interesting because to move from the idea into execution, it's very much a non-trivial problem. And we tried many different fundamental ideas, lift them up, move them apart. What's the energy yield differences? Bury them, put the frame in the dirt all the way,
So there's just glass on the surface.
So it's glass touching dirt. Right? I mean, there's many, many versions that we trialed. The idea of getting rid of the frame altogether, just using glass on the dirt. So there's many possibilities. But at the end of the day, you have to be practical. What's the available product in the world? And that's a, dual glass, crystalline silicon, First Solar's dual glass framed version. Those are the available product. And so using that, how do you hold them there? What do you do? So we did a bunch of tests. It was 2.5 years of testing and to prove, not just putting them together, putting them on the ground, prove the energy yield, prove the thermal conditions, very high temperature operating conditions, right? Luckily, I live in Arizona. So the first test ran right through the middle of August. And I remember it was 218 degrees outside. And the back of module cell temperature that day got to 76 C. I was like, the peak temperature is allowable is 85, right? And so it's not that I was surprised. It's a very difficult mathematical problem to determine, right? So while I wrote, did all the equations, you had to prove it. So I proved it in that first one. And I tried a couple of different combinations, but I proved it in that first.
What you're trying to prove is that there's not a significant degradation of the performance of the panel.
Temperature, the first one is you can't get over 85 C, ever. And that's just a fundamental criteria. Then this whole idea of damp heat and degradation, there's a whole litany of things down that path. But that first one, max allowable temperature, could we do that or not?
Right.
And prove that.
Airflow is
right.
Yeah.
Prove that.
Sufficient insulation behind the panel.
Before I brought anyone to the party of my own people that I've known my career, or before I brought any money from anyone, I had to prove that to myself.
Yeah.
And so I did. And I did that in my backyard just to prove it, right? The other parts of, there's dozens of questions that you can ask, but people don't really appreciate, and I learned this when I was at First Solar, actually, that modules are incredibly robust.
Oh, yeah.
Yes, amazing pieces of material. Amazing, incredibly strong and hard, taking shots from hailstones, rock, it doesn't matter, right? It was very impressive. They've always been an impressive object to me. The idea of putting it on the ground is, it's not that idea is conceptually novel. It's that people go, oh, you can't do that.
Yeah.
Right?
Conventional wisdom.
I was one of the people in the space that built these things, and I didn't think of it when I was in the middle of doing it.
Right.
And I was the type of person that should have thought of it.
Yeah.
And it probably, we crossed the threshold in about 2016, maybe, of when it made more sense to put it on the ground than not. So people have been moving this direction into the high density solar,
right?
B5 or 5B in Australia, PEG, right? There's different high density technologies and they're lower to the ground and all of this. But removing all the steel completely and going all the way to the ground, taking that final step, letting it get wet permanently. Those types of steps you can't do that.
Yeah.
I just started to ask the question, why not?
Yeah.
Why can't you do that?
Yeah.
Well, it turns out you can. And you just have to be willing to break the rules to truly find out. Once you've identified the aha, right? You've made the world's least cost electron,
right? Not
green electron, brown electron. You've made the world's least cost electron, period. And you've patented it. That's a very important step because you're able to control the playing field of the licensees and all of that type of stuff, right? You want to grow it and so on, but it is ultimately inevitable that the product will go on the ground because that's the least cost way to do it. So if you have that and you know it, what do you do with it? Well, one thing you do is you build a company to expand and build upon that.
To share that
and
technology.
To share that technology and do it. And we've been doing that. And that's where all the players of the company have come from. That's where Charles came from. That's where Daniel came from. That's where the various folks have all come from. But if you're able to do that, and it's truly cheap enough, the cost of that electron is cheap enough. And I believe there's a magic number in the cost of that electron. It's right at a penny a kilowatt hour, maybe 1.2 pennies, but right in that vicinity. If that electron is cheap enough, you can use that to make a portable fuel.
Yeah. What does it allow, right?
And
what does it unlock?
What does it unlock?
Yeah.
Right? That becomes the next evolution.
Yeah.
And so I realized that very early.
Yeah.
Because I have a big, long history within the space of energy and energy consumption and food and other things. So the original aha led to that next aha. And it wasn't very long after. It was pretty quick after. So it's like, okay, well, what do you do? How do you do that? Well, you got to build that solar company.
Yeah.
You have to.
Yep.
Because that's revenue.
And you got to surround it with people in the industry.
Surround it with people in the industry who know what they're doing.
Who have a track record of building projects and taking technology public, right? Bringing that technology to scale.
Get it over the technology adoption phase. Get it bankable. That whole word, bankability, is magic. You got to get through that process. I've been through it many times. I help facilitate Nextracker getting through it. Game Change multiple inverter companies, right? Certainly the first solar's module, right, in the U.S., built the first plants in the U.S., going through the, not just bankability and selling the projects and all that, but then all the local authorities having jurisdiction and getting through permitting and use permitting. And, there's so many, it's really complex, right?
So you were able to, a couple of years ago now, I did an episode at the time, sort of a coming out for Charles and Daniel Flanagan, formerly Zepp and Ojo, guys who have a storied track record of success in the industry, who are leaving very successful opportunities to come to this virtually unknown company, Erthos, to do this heretical thing, lay panels flat on the ground. And we talked about...
Well, think about Ojo. Ojo is a pile company.
It's a pile driving company.
The steel company.
Yeah.
And this is counter to that.
And Flanagan was a co-founder there of Ojo. To leave that to come, it challenged everything that I would say is conventional wisdom. And I had to know. 2 years ago, I interviewed them and I said, guys, I'm going to ask you, straight out, like, why would you leave what you're doing to come follow Jim Tyler's ideas around laying panels flat? And we'll link to folks to go listen to that episode. But the synthesis of the concept was, this is going to be the cheapest way to harvest electrons from solar, full stop. And we want to be a part of the team that helps deploy it. Made perfect sense to me. You've now sort of empowered that team. It's off and running. You've got Colin Caulfield coming over from Soltech to manage sales. You've long had Albie Fong helping you acquire projects. You've got hundreds of megawatts in pipeline and partners like Industrial Sun and Modern Energy, to name only a few.
We've got Betsy Engel as CFO.
Yep, you've got Betsy Engel as CFO. I mean, you've got an unbelievable staff that you have assembled to deploy this technology. And yet, when we spoke in preparation for this interview, the thing that stood out to me is you said, Nico, Erthos is not a solar company.
It's not just a solar.
It's not a solar company.
How is that?
How is that?
Yeah.
Tell me more.
So you have to go back in time a little bit for me personally. The first part of my career, I was in the food processing industry, designing and building very large capital equipment to manufacture food. In California, things like milk, tomato paste, other liquids, converting liquids to denser liquids, right? So evaporating water. That was the industry that I was in the beginning. Did that for maybe 6-7 years, and then I shifted into the semiconductor industry, became aware of semiconductor manufacturing processes all around the world. Right. And then within that industry, I moved out of that industry into a niche company for a short period of time doing film. Continuous roll film for some very high-tech problems, but it was continuous roll film out of Sacramento. And I recognized a balance or a merger between the technology that I was doing before in semiconductor, which was plasma etch, and roll-to-roll manufacturing, and joined those two. And we started developing that machinery that could do that. It turns out that specific combination of equipment happened right at exactly the same time as thin film solar. Thin film on film solar was being developed. First solar is off and away running when Germany is growing, and they're, 2006 or so, they're really starting to ramp. So I am designing and building machines for some of the early startups in thin film, Nano Solar, Mio Soleil, two examples. So I became aware of the market and what was going on. And I'm researching it because I'm making machines for it. And that awareness led me to OptiSolar. And I became aware that OptiSolar was going to build a factory in my backyard where I grew up. And so I applied quickly and got hired quickly. And ultimately became head of EPC and the development and the construction of our first factory in Sacramento. Well, it's just like serendipitous, right? That caused all of that background to lead to that. But as I moved through that, ultimately to First Solar and then to DEPCOM, it was the tie back to my original experience in food in California that is the thing that really, truly bridge the gap. If you're going to make a solar electron cheaply, like we had done,
Yeah.
what's the method that they use when they make food? And it's steam.
Yeah.
When you contrast all the energy forms in the country and the world, steam is one of the largest uses of energy, period.
Yeah.
Natural gas, burn natural gas, boil water, make steam. It's very common. It's actually used to make electricity.
Yep.
It's used to make food. It's used to heat houses and big buildings and all kinds of things. And in the portion of my career, I did that a lot and got really good at it and understood it. So when I started thinking about the problem for Erthos, we can make this really cheap electron. Can we take that and make steam?
How do you take that electron?
What's the transfer from one to the other?
Yeah.
And what's the price point?
Yeah.
And does it make economic sense? And by the way, this is all pre-IRA.
Right. Yeah.
Pre-IRA thought processes, pre-Series B. I'm going through these processes. So fully aware of the hydrogen, what's going on. And it was starting to make quite a bit of noise.
Yeah.
Nell and Plug and Ohmium and all these different companies. And I start looking at them and say, okay, well, I'm going to inject the very cheap electron into water. I'm going to make hydrogen. I'm going to store that hydrogen. I'm going to use that hydrogen to burn it and make steam 24 hours a day for these food processes.
Wait. So Erthos is a hydrogen company.
Erthos is a energy technology company. We've developed the solution to replace fossil fuel in combustion. That's an important feature.
Yeah.
The solar is a means to an end.
Yeah.
You have to have the solar.
Because you need the cheapest kilowatt
Because
hour.
you need the cheapest kilowatt hour. And it has to be a penny.
Yeah.
It has to be a penny.
Yeah.
Well, what's the LCOE of
An unsubsidized
electricity?
penny, preferably.
Right. So what's the price of a solar in the United States today? It's about 3 to 3.5 pennies.
Yeah.
Right. I mean, LCOE, somewhere in that vicinity.
Yeah.
So you get to a penny, there's a lot of things got to happen to get to a penny, right? Especially unsubsidized. But if you take the solar panel, an unsubsidized solar panel, a non-tariff solar panel, and you put it on the dirt without any racking, and you just look at the electrons coming out of that panel, and you put it in a really good sunshine spot, Atacama, you put it there, no brainer. You put it in someplace in New Mexico, no brainer. It starts to work, right? You're starting to creep up on the penny. You're at about 1.2 pennies, frankly, with a solar panel just sitting on the dirt. So now you're into the arena. If you take that 1.2 pennies and say, well, how much energy is in a kilogram of hydrogen?
Right.
At a penny, it's 100% efficient conversion. It's about 34 cents a kilogram. That's the electricity cost at a penny. If it's 3 pennies, it's $1.
Yeah.
If the price of the electron going into the hydrogen is 3 cent pennies, then it's $1 just for the electricity price.
Yeah.
That's at 100% conversion efficiency. So you're still like a long way. You got to get the hydrogen to $1 in order to compete with natural gas and combustion. So it's like, man, we're a long ways away, right? But you got to start somewhere.
Yeah.
So I started seriously looking and just challenging the ideas, very simply challenging the ideas. So get the prices of electrolyzers from Nell and Ohmium and Plug and look at that price. And I'm going to make this super cheap plant in California at one of those food processors. I've got good relationships there. We're going to do a gigawatt scale project to replace steam.
To replace steam produced by natural gas.
Produced by
with
natural
steam
gas.
produced by hydrogen.
Correct.
Every article you read today, from Europe to Australia to the hydrogen hubs of the US, says that hydrogen is dead. And in particular, Trump's coming into office, hydrogen is on the chopping block. How do you, as an entrepreneur, how do you square that? How do you justify moving into a technology arena where Rafi, I think, has raised like over $100 million?
More than that.
Yeah. It's probably closer to $500 million. You would know the exact number.
He's got the same investor I do.
Capricorn.
So invest in both companies.
So it seems like headwinds, it feels like solar is becoming more expensive, not less expensive in the United States, especially in a tariff-laden economy where every manufacturer, at least that's credible, is bringing their plants to the U.S. The price of a domestic module is going up, not down. So talk to me about like the holding that vision for not just a solar company, but a solar company that leverages hydrogen technology. And I'm actually eventually curious to hear sort of how. I mean, are you in partner with your buddy Rafi? Like, how are you going to actually convert those electrons?
So you start with the cost of the electron itself.
Yeah.
You have to start there. If you can't get it to that penny or close to it, starting to scare it, just stop.
Yep.
Right.
And so we're there with Erthos.
So we're there with Erthos, but you're there with Erthos in a special way. You can't convert it to AC. You got to leave it in its DC form.
Ah, I see. Okay.
Magic.
So before the inverter.
Before the inverter.
So if you remove the inverter from the process, then you're down to almost a penny a watt delivered.
Remove the inverter.
DC electron.
Let's go through the steps. Remove the inverter. Remove the transformer.
Right.
Remove the distribution.
Right.
Remove the substation.
Yeah. There's no interconnection point.
There's no interconnection point, right? You remove all of that. If you contrast the CapEx cost of a solar plant, you say, what is the AC cost in a solar plant?
Right.
Because what I'm describing is you remove it all.
Right.
Okay. In an Erthos system, it's about 18%. All in, 18% of the cost of the plant is AC. But you do something else, and this is where people don't, the yield per panel, there's a thing that we all know, it's called DC-AC ratio.
Right.
DC-AC ratio is intended to utilize the AC hardware at a higher capacity.
Right.
Right? So if the solar panel was free, if the total DC array was 0, you would put so much of it out there, you'd get 100% of the yield out of the AC hardware.
Right.
That's the whole premise behind Erthos from the outset anyway.
Right.
So now you remove all the AC hardware, the yield of the DC plant, because a typical Erthos plant will do about a 1.8 ratio in the US.
DC to AC.
DC-AC ratio. That's where we're optimized. The tracker is about 1.3, right in that vicinity. So at a 1.8, we lose 21% of the energy in clipping annually. You get all that back. So not only did I reduce the first cost of the plant by 18%, I increased the yield of the DC array by 21%.
But now you got all these DC electrons. You're not putting them in a battery.
Now I've got all these DC electrons. Well, how do electrolyzers work? Electrolyzers have been around a long time. Electrolyzers have been around a lot longer than solar panels have. Oh, yeah. Right? I mean, 400 megawatts of electrolyzers in New York State, around the Niagara Falls, 1904, right? Big electrolyzers, been around a long time. People proved it, know how to do it, created all the tools, parts, pieces. So there's a tremendous amount of working knowledge, patents, history about it.
Bankruptcies.
But water electrolysis, fundamentally as a technology, is not new at all, right? Especially alkaline-based electrolysis. That fundamental technology is actually amazingly simple. Take 1.5 volts, dunk it in water, you make hydrogen and oxygen off the 2 leads. Now that's the simplest. So now it's not that I'm trying to invent something simpler, but kind of the same way if you think about Erthos is we removed all the things that you don't need to make and still make the power. Right? Can't you do that with the electrolyzer? Remove all the things you don't need. Well, the electrolyzer uses DC power out of the gate. The electrolyzer has an IV curve, just like solar panels have IV curves. Solar panels are not batteries. The voltage and current change with sunlight, but they change relative to the resistance, the load they're connected to. They try to operate at the maximum power point. That's what the inverter does. Well, if you connect it to an electrolyzer, all the electrolyzers You can think of an electrolyzer as 3 parts. You can break it into 3 big parts. Power electronics, the business end where it splits and does the work, and then gas refinement, where it refines the gas to high purity hydrogen.
Right.
Those 3 steps, right? Approximately 1/3, 1/3, 1/3 in cost also. And these aren't numbers that I've come up with. This is NREL's published. There's a lot of variance all over the board, so there's no perfection there. But generally speaking, if you say, well, hell, let me just take all this other stuff away and just use the business end, the electrolyzer in the middle.
Don't need to purify it. Don't need the power electronics.
Right. How would I connect the solar panels to it and make that thing work? Well, you've got to design that thing to match the output of the solar panels. That is simply a math problem. It's a very well-defined mathematical set of equations, both for the electrolysis side and for the solar side. Extremely well-defined, in fact. So you can write all these math equations, put it all into an 8760 calculation, and determine how you should design the electrolyzer to match the solar panels.
To match the load,
To match the load is the electrolyzer to the generation. And then optimize that design, right? And that's what we did.
8760 for the uninitiated is the amount of sun hours in a year.
So that process took a year and it was strictly mathematical problem, Excel spreadsheets and researching and understanding, right? But it turns out it's just strictly a math problem. You don't have to invent something new. I don't need to invent some ultra high current debounce problem and the diaphragm in the electrolyzer of the technology of the diaphragm or the electrode. Just use what's existing. What does the market use today? Same stuff. Or what did the market use 100 years ago? Even simpler. Right? We've gotten it. Just because you enhanced technology doesn't mean it's necessarily the right thing to do.
It
improved. So it turns out the solar panels operate, essentially 1200 volts average voltage, 1500 max, 900 min. That's the voltage. Electrolyzers split water. If it's 100% efficient, about right at 1.5 volts. Well, how do I get 1200 volts to 1.5 volts? Kirchhoff's law says a voltage divider, right? A series of resistors. All an electrolyzer is a set of cells that are all resistors.
Rectifier,
That's it. It's actually a very straightforward math equation. Design it accordingly. So we did. Made one. Proved it.
Made one what?
Made an electrolyzer stack that was exactly sized to the solar panels of a string that operates at 1500 volts.
So instead of the power electronics piece that basically harvests or creates the power, you replace the power electronics with solar.
Rephrase it. Rather than the power electronics have to take the electricity from the wall or from the grid, convert it down, step down the voltage, transform it.
To 1.5 volts.
Well, that's to transform it to DC from AC. Then you have to rectify it from high voltage, high voltage DC to low voltage. That increases the current dramatically, massive current. And high current is actually a good thing in an electrolyzer. Current density is an important feature of an electrolyzer. But if the solar panels are making 1500 volts, what's the right answer? What's the right math problem? Because at the end of the day, it's levelized cost of hydrogen, not levelized cost of electricity. So you got to design your electrolyzer to be as cheap as possible, absolutely minimum cost, because it's only going to run when the sun is shining. So if your typical capacity factor is 24/7, 365 connected to the grid.
And herein lies the conundrum with most companies, including Rafi's electric hydrogen.
That's right.
Is that you need an 85+% utilization rate to make it economically.
Get it even close. Well, if you just throw that idea out the window, just say, I don't need it. I just have this solar.
I get to work with what I get.
I get to work with what I get.
Yeah.
Now what?
Okay.
The cost of the electrolyzer matters. It very much matters. It has to be unbelievably cheap. So what's the cheapest thing you can make? Well, the least expensive, but still does the job, does what you need to do. If you remove all the power electronics, the transformer and rectifier and all the things that convert the power ready to go into that electrolyzer at that right voltage and control it steady state for 24 hours of operation, you remove all that stuff, it removes a third of the cost of the whole of the electrolyzer, just doing that step.
But it also improves the efficiency, because one of the biggest arguments is
you lose energy
is
through
that you have to do all this energy conversion of the electricity.
You lose about 3% of the energy in that conversion. So you gain that back.
Are there electrolyzers that use a DC input on the marketplace, or are all electrolyzers AC input?
I was unable to find one.
A DC input.
A DC input electrolyzer.
Okay, so if we just stop there, every solar plant being designed right now with the intention of injecting that electricity or those electrons into some sort of a hydrogen economy or process are losing energy, converting it to AC, and then converting back to DC. We just had this discussion with Dynapower about doing the same thing for batteries. Right?
And the first cost.
Our whole industry is built on the inefficiency of AC coupling technology. Thank you, Edison. So,
well, that was actually, thank you, Tesla. Edison was DC. Tesla was AC. Tesla was always about transmission.
I thought Tesla was DC.
It's the other way around. Tesla's AC. He made the motor to able to make AC to create the transformation so you could transmit power cheaply.
Yeah. To be able to get
Edison wanted DC, but transmitting DC at a distance, difficult to do. Yeah. Ultimately, today we are doing very high voltage DC, and that works, but he didn't have that back then, right?
So now we've established the problem. There's a conversion issue, and that actually dramatically increases the cost for hydrogen conversion if what you're working with is AC electricity.
That's correct.
Okay.
Yeah. Now you're getting very high utilization.
Right.
Because
you can use any input.
Because you're using any input.
Right.
And that's fair versus the DC input. But if the cost of the DC input is cheap enough, and let's say for sake of discussion, you're getting 22% utilization.
Right.
On an average annualized basis for the DC only, you're getting
that's
DC
a low
energy.
Number.
It is, but that's actually the DC irradiance or DC input if you put solar PV flat on the dirt.
It tells me that if you could get that low and make it economically feasible, you have 80% upside because now you can figure out other uses. Now we're with hydrogen in the same place we were with the electron.
If I take the DC and put it up on a rack and tilt it to the sun, that's good and increases the DC utilization, no question.
Yeah.
But the panel in Australia is 8.5 cents a watt. The rack is 10.
Right.
Do I increase the yield of the panel by 100%?
Right.
No. I increase it by maximum 30%. Maximum. And land utilization, right? All those things. So anyway, back to the point. You remove all that conversion, power conversion equipment. You reduce the CapEx dramatically, and you increase the yield out of the solar plant into that. And you increase the efficiency up to the point of the stack, right? You've eliminated about 3% losses through the transformer rectifier. So now you're into the stack, and I want to come back to the stack here in a minute. I want to talk about the post-process.
Yeah.
Everyone in the world today thinks about hydrogen, one product, high purity hydrogen, 5 nines. It's the only, when you talk about hydrogen, everyone's automatically talking about that.
Yeah.
Okay. And you use it for 2 things. It's used to make ammonia, to make fertilizer, and that's 47% of all the hydrogen consumption in the U.S.
Yes.
And then you use it to make gasoline, to crack gasoline into the different levels of refining in gas.
Yeah.
Those are the 2 applications. The gasoline is 53% of the hydrogen, and the ammonia for fertilizer is 47% in the U.S.
Yeah.
So,
and that's for existing hydrogen. That's not hydrogen replacing methane. That's not any other.
That's existing hydrogen.
Not replacement technology.
That hydrogen, all of it comes from No, it all comes from methane.
It comes
natural
from
gas, and it comes from steam methane reforming. It's been around for 60 years, 70 years, steam methane reforming.
Yeah.
So, and you use that hydrogen to go do those chemical processes.
Yes.
Those are chemical processes. They're not combustion processes.
Right.
They're very different. So you need high purity because it's a chemical reaction that you're doing. Okay. My mindset wasn't on that problem at all.
No.
Out of the gate.
Food.
I want to burn it.
Uh-huh.
I want to make steam.
Yeah,
I want to burn it.
You want to burn it just like we're burning the methane.
So when you burn hydrogen, if you burn hydrogen with air is, 20% oxygen, 80% nitrogen. If you take hydrogen, you burn it with air, what do you make? You make water. Hydrogen, oxygen makes water. And that combustion temperature is so high that you take the nitrogen in the air and the oxygen in the air, and those two join, and you make NOx.
Yeah,
you make NO and NO2 and various things.
Yeah.
When you make that, it consumes some of the energy from the hydrogen combustion. So you don't get all the benefit of the combustion of the hydrogen when you burn it with air. And you make NOx. And NOx is 300 times worse than CO2. Right? So people go, oh, I want to make hydrogen. I want to put it in a natural gas pipeline. I want to increase, in that methodology. And all you're doing is you're taking the natural gas and you're increasing the efficiency of the natural gas boiler and all that. But you're
also increasing your greenhouse gases.
Yes. So I wiped the slate clean. If you want to burn hydrogen and combust it, you should combust it just with oxygen.
Yeah.
If you combust hydrogen in a pure oxygen environment, you will only make water. That's it. If I'm going to combust hydrogen, why does it need to be 99.999% pure in the first place? Because when I make the hydrogen through electrolysis, the other part of the impurity is oxygen. So let's say I made 99%.
Because that's part 3 over here, which is what cleans up the hydrogen.
That's right.
That's the other third of the cost.
That's the other third. Now that equipment is generally known as PSA, pressure swing adsorption. PSA is used to make hydrogen in the natural gas processes. It's very well known, very well understood, nothing magic, right? When you do water electrolysis, the electrolyzer has a part of it as the PSA. That's a part of the electrolyzer.
Yeah.
So again, I said there's the front, the middle, the back.
Yeah.
The PSA is about a third. It's not quite a third. It's maybe 28% or something like that. But it's a component cost to the whole of that electrolyzer. The electrolyzer gets bigger. It's a less expensive part, right? So you can move things around. But generally speaking, it's a component cost. And it consumes energy. You got to compress the hydrogen in and out of multiple swings of pressure to get to that refinement. If I don't need to do that, if I just go 99% pure, I can eliminate that part, right? Now when I've got my hydrogen 99% pure, I also have oxygen. I made it. Nobody collects the oxygen when they make hydrogen in an electrolyzer. They just vent it to the atmosphere.
Yeah.
Why not collect it? You've made it, just collect it, and then use it as a part of your combustion process. Now, when you combust those two, you make water, and that's it. But you make water in the form of water vapor. You don't make liquid water, you make water vapor. If you take that water vapor and condense it back to liquid water, there's another piece of magic. You get to use what's called the higher heating value of hydrogen rather than the lower heating value as the energy content in the hydrogen, if you go all the way to condensate. So the process of combustion, then use the condense process to preheat the incoming water, you get that energy back. How much energy is it? 20%. You increase the energy content of the hydrogen by 20%. It goes from 33.3 kilowatt hours per kilogram to 39.4 kilowatt hours per kilogram. And it's free. It's just there. Nobody uses higher heating value in the whole industry of hydrogen ever because you don't combust it.
Yeah.
And if you combusted it with air, you don't get to do that because it's hard to condense the water out of the air combustion process. But if you have just pure oxygen and it's already there, it's easy. It's just right there. And it doesn't need to be high purity. It can be 99 each.
Yeah.
That is magic because now I've removed the last third cost of the electrolyzer, the energy it takes to consume to do the PSA, right? And I have two commodities, hydrogen and oxygen, rather than one.
Yeah.
So now we're into the electrolyzer stack by itself, just the part in the middle. I've optimized the design of that, put the DC into it. I'm only taking these two gases. I'm taking both gases out, but at a lower purity, right? So now you're into a different set of questions where you're into, say, I want to optimize this stack for its cost. Pretty common. So first off, the fluid in a atmospheric or alkaline electrolyzer generally is potassium hydroxide. Highest efficiency potassium hydroxide as the electrolyte is about 25, 26%. You want all these parts and pieces. So we're not inventing anything new. We're just doing what they've done for 120 years, right? Same stuff, right? And then designing that electrode to do this work. So now it's just about separating those gases to 99%. So there's the magic part in the middle called the diaphragm. And everybody's got to separate these gases for that diaphragm, or with using the diaphragm. Well, a long time ago, those diaphragms were made out of asbestos. Today, they're made out of zircon, and then other things for PEM and different types of electrolyzers. But generally speaking, that part, just like the transformers and rectifiers, not only are they expensive, they're really long lead time to get them. The same thing's true with the diaphragm. It's a long lead time part. There's rare earths in it. So attack that. First way to attack it, get rid of it. And I just get rid of it altogether.
Why get rid of it? How do you accomplish what
separation?
The separation without it.
So again, this goes to fundamental first principles. Why did you separate in the first place?
Because you needed to get 5 nines.
Because you wanted 5 nines. So then I said, well, then, but high purity versus low purity hydrogen. What if you just left it together?
Right.
That's kind of a crazy what if.
So the fundamental leaving it together is why you don't need the diaphragm.
It's a premix, right? Can you burn that premix?
Right.
That premix has a name. It's been around for a long time.
Bang gas.
One name is null gas.
Yeah.
Another name is bang gas, hydrox, oxyhydrogen.
Yeah.
There's a bunch of names for it. It's been around for a long time. It's dangerous. It's highly combustible, right? So you don't want to compress it. If you put it in a tank and compress it very much, you have a fairly dangerous object, okay? But you can design tanks to do to a certain extent, maybe 60 PSI would be fine, but you gotta, this is now, if I made that type of gas when the sun shines, I gotta consume it when the sun shines.
Right.
I can do that.
Certainly.
There's no reason I can't consume that hydrox gas just while the sun's shining. Speed up, slow down. Make steam, connect that steam to a steam header, and now all I've done is offset the existing natural gas steam header with this type.
Yeah.
It's the cheapest possible, period, no question.
So you've been in the food industry for a long time. Your father was at Campbell, and you've had a lot of conversations with the buyers who pay for natural gas in California. Talk me through the economics then of offsetting natural gas for steam.
So you got to start with the price of natural gas at Henry Hub. That sets the price of natural gas for the world. The cheapest it's gotten down to is about $2. It got up to about $9
MMBTU.
a dollar per MMBTU. MMBTU can be converted to kilowatt hours, megawatt hours. But so it got up to about 9 at the height of COVID and just after COVID. But when you're at Henry Hub, that's the industrial price at that point, right? That's kind of like the nodal settling price.
There's still transportation price.
When you consume it at industrial consumers, at that final industrial consumer, big plants consume a lot of the natural gas. In California, specifically for some of these industrial consumers, the average price over 2022 and 2023 was about $7 an MMBTU. You take that gas, you burn it in a boiler, and you make steam. You lose efficiency through the boiler. So you really got to look at the price of the steam instead of the price of the natural gas. Okay, so you got an efficiency conversion through the boiler. So if the MMBTU dollar price is 7, the price of steam post boiler is about 9. It's about right, and 7 is a reasonable price.
So you have to be able to deliver steam.
You got to be able to deliver steam at 9. If you deliver steam at 9 in California, you win. Period. Because the price of food is ubiquitous. It's global. Everyone buys food. Just because I can make it for this price doesn't mean I buy it for that price in the U.S. But the cost to make the food is very similar all around the world. California has to compete with the whole world for making food. They do it well. It produces 25% of the world's tomato paste, for example. I know that number because of my history. But
higher percentage of that for milk, I think.
Milk is a larger commodity coming out of California. The energy demand to make tomato paste in California, just tomato paste, is between 12 and 15 gigawatts. 12 to 15 gigawatts equivalent of natural gas.
Oh my goodness.
The entire grid of California is 35 gigawatts. Just a single commodity consumes 35% of the equivalent of the entire electric grid in California. People go, what? No. Yes.
How can that be?
Yes, that's actually what it is. I could build 15 gigawatts of solar to hydrogen to replace the natural gas consumption in that commodity. The volume of solar to hydrogen is astonishing. If I'm able to do that, I don't have to connect to the electric grid to do it. I remove the constraint for solar. The growth rate of solar in the United States is directly tied to the interconnect, the ability to connect it to the grid, the speed with which we can ramp. It was 2 years. Now it's 4 and more on average. It's 4 in ERCOT. It's more than that in most other places. That's a speed limit. If I don't have to connect it to the grid, if I can make the hydrogen off-grid
on-prem,
and then consume it, right? Especially if I don't have to transport it, if I can do it, locally made. So the California and Texas markets are exceptional for that. Because plenty of sunlight in both places, lots of demand in both places for steam-based applications. Massive demand. Bigger than the total demand of electricity, right? So I recognized all that, and you start breaking these things down. You get back the higher heating value of hydrogen. There's one other crazy thing that you get back. When you burn hydrogen and oxygen and you condense it, the boiler of a pure hydrogen oxygen boiler, that's another piece of magic. Nobody's ever made one. They never made one because hydrogen's too expensive. It didn't make sense to make one. So I go and got my background with the guys and people that I know from the industry, and let's make one. We have one. We've got a 11,000 pound per hour boiler, 11,000 pounds an hour of water to steam. Convert 11,000 pounds of water
per hour
to steam in an hour. We have that boiler fully operational. Fully operational.
Can I see it?
Yes. It's in Sacramento.
Can I go see it?
And it burns hydrox gas, hydrogen and oxygen together at about 45 psi. And it speeds up and slows down
based on the sunlight.
And I can directly replace the steam in the header with that at a price point significantly below $9 an MMBTU.
Okay, but But food plants run 24/7.
Yeah.
So it's a dual coupling. You're offsetting the cost. You're lowering their annual cost, but you're not replacing the entire steam system.
So if you did it just while the sun shines, you're only going to replace so this is a summertime operation generally for that type, you're only going to replace about 25%, right? Nothing prevents you from taking those two gases, compressing them, putting them in a tank, and then using them 24 hours a day. Nothing prevents that. So, and that technology exists.
Sure.
Okay, so the pressure...
Betsy just worked at a company that has
the pressure of those tanks, there's an optimal pressure for those tanks. Run all the math. Here's the price of the tank and how much it stores and the compression ratios and all that type of stuff. About 300 bar, which is 300 times atmosphere, about 4,000 PSI. I can get 2 days of storage in a tank. The cost for those tanks, 2 days of storage per gas, 12 cents a watt. For 2 days, that's 48 hours of storage.
Right.
For 12 cents a watt for each gas. I'll let your brain run the math on that problem versus batteries. It's bananas. Compressed gas absolutely works. No question. Because I don't need to store it for 6 months.
Yeah, by the way, the reason people have said
effectively 2 days.
Hydrogen is an efficient battery, because that was one of the original, like 3, 4, or 5 years ago, the hydrogen boom is going to be a battery replacement, is because of the conversion losses. Didn't make sense. Why would we use hydrogen in the battery? We still have to convert it.
You run hydrogen compressors.
But if you
take what I'm describing at 99%, hydrogen oxygen compressors, you compress them, put them into those tanks. It only requires the equivalent of 2 days at peak production worth of storage.
But again, we're not talking about converting electrons, DC to AC, and then creating hydrogen, and then converting the hydrogen back to electrons at some other point in the future.
You're combusting it to get the heat out of it in order to boil water to make steam to compete with. So here's the last little point, by the way, that boiler, when I was talking about that boiler, what's the efficiency of the boiler? The natural gas boiler, when you burn the natural gas, some of the energy goes out the stack. About 20% goes out the stack. The boiler I'm describing is fully insulated. And the only material that comes out of it is steam and the condensed water, back to liquid water.
Right.
There is no effluent at all, zero.
Is that condensed water distilled water?
It is. It's perfectly distilled water. And it has a name. It's called fire water. Kind of an ironic name, but starts as fire, turns into water. We condense it. We get all that energy back. The efficiency of the boiler, 98%. I get 18% more energy back than the natural gas based. I take that fire water, which is perfectly clean liquid water, and I put it back in the electrolyzer.
Yeah, of course.
Now I don't need new feed water for the electrolyzer. I fill the system up one time, closed loop.
Perfectly closed loop.
Perfectly closed loop. Now the electrolyzer does not build with contaminants. Because the water you put into the electrolyzer is not clean. It'll have a TDS of 60 or so. Over time, you have to clean the electrodes, right? You have to clean the diaphragm. If you're putting in perfectly clean water over and over and over, they don't contaminate. Reduces your O&M cost. So you got to put all of these things together, right? I can't go, oh, I'm going to buy this electrode. I'm going to buy this part. I'm going to buy this part. And I'm going to be a developer who's going to develop a project and figure all these things out.
But a traditional solar developer is not going to figure this out.
Hell no. You need all these things.
The Venn diagram of raised in a household of a guy who works for Campbell's Food, early career in the food industry, over to silicon. Because we still haven't gotten to the important, like the key point. Like you're just talking about steam replacement as an economic justification for building an electrolyzer.
If you solve that problem of making the steam to make food, if you're able to financially solve that problem, which we have,
Right.
you solve all the other problems.
Sure, it's economic justification for the rest of the problem.
The rest of the
rest of the machine.
So I can take that hydrogen that I would have made there, and I can refine it.
Sure.
I can put it into a really big PSA.
Sure.
Right? And make high purity hydrogen to make ammonia. No problem.
Yeah.
The cost of that hydrogen will be about $1.50 a kilogram.
Okay.
The cost of brown hydrogen from, $4, $5 gas is about $1.40 a kilogram. Mm-hmm. I can make green high purity hydrogen right at parity with brown hydrogen from natural gas. Right at parity. Today. Absolutely. So now you unlock all of that,
mm-hmm.
right? And everything I can take that high purity hydrogen, I can compress it, put in a car,
sure,
and run the automobile,
mm-hmm.
already existing automobile infrastructure.
1999 GM would be very happy with that.
The company that went bankrupt because of hydrogen would be very happy.
Yeah.
Right? Mm-hmm. So you solve this problem, you solve all the others. Mm. So that's what the focus has been.
Sure.
I recognized this a long time ago. This was, 2.5, 3 years ago. So it took a long time to develop all these things. So we've developed the boiler. We developed the electrolyzer stack that's DC coupled and designed.
Created your own Erthos electrolyzer.
Created that structure from scratch, right? The infrastructure between it to compress it and all of that. Because this is, these are off the shelf parts and pieces. Sure. We're not creating anything magic. And frankly, the electrolyzer, we didn't create anything magic there.
Yeah.
We didn't invent a new material electrode to do this efficiency thing, or we didn't create a high frequency DC bump in the thing to cause electrons to bump free to increase the efficiency. We didn't do any of that shit.
Right.
We didn't have to. We went to the fundamental, simplest forms. Stainless steel, the raw material, 316 stainless, at low temperature, low pressure, and high-density polyethylene. The electrolyzer stack itself is so fundamentally simple that we get the cost so cheap that we can make it here in the U.S. for extremely low prices. But do I want to sell the electrolyzer?
No.
No. That doesn't make sense at all.
Because you are a hydrogen company.
Sell hydrogen.
Yeah.
Develop the hydrogen. I can't take all of this technology and go to Mr. Developer,
right,
who's developing a project of hydrogen. He's going to want to buy this company and this company and this company, and he's doing all that work. So it'd be very difficult for me to go, to sell to developers this idea.
And also they're going to try to commoditize your
that's right.
technology.
That's right.
They're going to make you compete with any other electrolyzer in the market. It's not the same.
It's not
apples to apples.
It's not apples to apples. So if we sell hydrogen or sell steam,
I
can sell steam directly. Steam purchase agreement.
Does that exist?
They do. It's an interesting. There's companies, energy services companies that do steam purchase agreements.
Okay.
But one of the beauties of a steam purchase agreement, though, for this is the price of steam fluctuates based on the price of natural gas.
Of course.
The most you're going to get is 1 year ahead futures on natural gas purchases. Wow. So the price of natural gas can go up or down.
You can stabilize CapEx or OpEx rather.
Flat. For food, the cost of electricity or energy is 15% of the cost of the food.
Of course. Makes sense.
And you stabilize it, make it flat.
Yeah.
In California, they can't burn any more natural gas. They're capped. 2022, AB 32.
How much is transportation component of the cost?
If you co-locate these plants, then the transportation's zero.
No, I meant of food, right? So 15% of the cost of food is electricity.
Oh, that's wild. It's all over the place. Depends on how far you ship it. And
because my assumption is the question is, then why would anybody create food in California at all? And the answer is because the raw materials are cheaper.
The land, the water, and the cost of natural gas.
Yeah.
Those three things, that's why they make it in California.
Got it. Talk to me about the process as an entrepreneur that you went through to validate this idea post-pandemic. You pitched to the beginning of the pandemic, how did you mobilize capital around this? Because you're not, you're not a billionaire like some of our friends. You have had a successful career. You've built tremendous relationships and deep knowledge and subject matter expertise. How did you mobilize capital around that? Talk to me about the timeline of stacking capital, like prioritizing around what you knew you could get funded so that you could move as an entrepreneur from win to win.
Erthos fundamentally is not a heavy duty CapEx demand as a company. We don't need a big manufacturing facility to make something. We don't need, the majority of what we do, we can source the supply. Right. So our burn, our monthly or annual burn is basically headcount. 83% of our burn is people. So you want to bring in obviously really good people, people that believe in the vision, trust in that vision, understand it. But you also want to focus to start to make enough revenue to pay for that headcount. That's just the standard business model of startup companies, right? So the solar business is that. Create the solar business, start doing this.
Create something that can be sold.
That can be sold, right? With the minimum demand on burn. So that was the initial premise of the company. Carte blanche.
Got it. And that's what we talked about in the very beginning. Lay panels flat on the ground.
That's the baseline.
Reduce, eliminate racking, and introduce an alternative opportunity for developers who can make more money through this application. How much and how long did you have to wait from inception of idea to first dollar back in from a sale?
So it took us 2.5 years to develop the IP, figure it out, make all the parts that would be necessary, sufficient to introduce it to the world. We weren't done when we introduced it to the world, but we were close enough that we knew once we introduced it, then we'll be able to, finish it as we go, right? But as in any technology adoption in the solar industry, the utility scale solar industry, you have to prove it. And it's not that we created a new technology. You take the existing technologies and put them on the dirt, right? The proof is all about, will they survive being on the dirt? What's the energy yields? What's all these other things? So we had to start small, get our first project, which we bought.
Put one in the backyard of Mr. Samulian and Paso Robles.
That's one, right? That was actually the third one, but the first one was in my backyard. The second one was in Bakersfield. The third one was in Mitch's backyard. And Mitch was an initial investor in the company. Right. So, but nonetheless, that second one in Bakersfield was really important. So we bought that asset from a developer that we knew.
A project, an interconnect, an agreement with an off-taker.
It was a shovel-ready project. Off-taker was a farm. Interconnect PG&E. The developer was White Pine. Right?
Okay.
So WPD, White Pine, WPD. So he had an asset that was underwater. He was going to have to build it with a tracker, and he couldn't make money. It's about $65 a megawatt hour. And it's pretty small, only 300 kilowatts, but he wasn't going to be able to make money on it. So I bought it from him, but I paid him a dev fee, positive dev fee. And then we built the plant, and we were able to build it and sell it. And that company that bought it, with all the tax implications, that company was cash positive after 2.5 years. We made a profit of 20 cents a watt for us. Aggregate, all in.
On a project that was upside down.
Totally upside down, that was just going to be jettisoned by the developer. But for us, it was the first project that we put in. So now I can prove temperature, water, blah, blah, blah. And it was in Bakersfield, 110 degrees. So I
want to pause for a second. For anybody who's not familiar with the industry as insiders, this is no developer, they didn't know what they were doing. This is one of the most experienced developers. Former president of Calcom, the single-handedly best developer in the state of California for projects under 20 megawatts. Hands down.
To be clear, he had bought a portfolio of projects from another company.
Sure. And so you had to
And
figure out
that
what to do with
was
this.
one of the
It had hair on
portfolio
it.
projects that
Yeah.
wasn't viable.
Yeah.
So he had to find a way to
Of course.
either jettison it or make money.
Amazing.
He made money,
Amazing.
right? Well, he also got stock in the company. Even better, right? So, so that's your first one. You got to start small, work your first one. Well, then we did it again about a year and a half later. We bought another 5 projects from the same guy.
Yeah.
Paid him more money for them. But that time now we've proven the technology, but we've been changing the technology. We've been making tweaks and tweaks and tweaks to parts and pieces. Those 5 projects have now been in operation for over 2 years.
Yeah.
The single project over 3 years.
And where did you get the capital to put the team together and to buy those projects?
So first capital from myself and from the very first employees, put money in, Charles, Daniel, Keith Simmers, a few of these folks that came in the beginning, Mitch Samuelin, about 800,000. That's the seed capital, right? The Series A came from a combination of people. The dominant portion of the Series A came from the company that ended up buying those assets. He's also the largest electrical subcontractor in the country.
Wow.
Solar electrical subcontractor. His first electrical subcontract was for me at DEPCOM.
Wow.
He hadn't built any solar plants before. And we gave him a $7 million deal, and he did it and did it well. Now they are they're at like 1.2 gigs a year as an electrical sub. Just pure electricals, not an EPC, just an electrical
company
sub.
is that?
DSI, Directional Services, they're now called Centera.
Okay.
They sold their company for $100 million. Very good sale. I mean, that relationship helped to, it made them, we'll invest in Erthos and we'll buy these assets from you. So it was a win-win.
Yeah.
So they invested, and then I received some Series A from a series of investors from my prior DEPCOM.
Yeah. Friends and family.
No, these were angel investors. Okay. Angel investors. There's a series of 9 of them.
Okay.
In a consortium. So we raised another $5 million or so on that. And then we sold those assets, made profits on the sale of those assets, right? But we're also skinny. You don't, you can go raise a whole bunch of money.
Right.
And when you raise money early, you're giving away a lot of equity.
Yeah. And a 5 million Series A these days is small.
Yeah. So, same thing happened when we started DEPCOM. The employees owned 65% or so of DEPCOM when we sold it. Well, same thing's true with Erthos to this day. Employees own about 60% of Erthos. Wow. Well, the only way to do that is you got to be tight with the money and tight with, but you also have to recognize the value of the company is rising with time. So, as you go through the process, the higher the value of the company, the lower the dilution as you bring in new money. Mm-hmm. So you just want to be stingy with the rate of new money add.
Right. Mm-hmm.
Well, the Series B happened with Capricorn. Right. Jan Yadagroglu is the original founder. He and his partner Depender of the Capricorn's first fund. Well, that first fund was an investor in DEPCOM. So I became aware of them at that phase. Mm-hmm. They did really well on their first investment. They were a Series A investor in DEPCOM. We exited at the E, right? They made a 35 multiple, something like that. So it was a pretty good return. But along the way, I started to have interactions with Jan around some of his other investments as an EPC. So when I called him for the Series B and tell him what we're doing, he became very excited very quickly.
Right.
I'm guessing it was brilliant.
And I'm guessing that conversation had a lot more to do with what we've discussed over the last hour about hydrogen and less to do with.
Well, actually, it was the other way around. It was all about the solar in the beginning. I didn't have the full knowledge of the hydrogen when I did the Series B with him. It was in the back of my mind, but the dominant conversation was the solar.
Yeah.
So now here's what's really interesting. Capricorn's review team, brilliant team. One guy in particular, Jim Lyons, was the head of R&D for GE for 30 years. That guy has seen more than you can imagine.
Yeah.
I mean, he really has. He was the one who did all the diligence on Erthos and understand all the parts and pieces around that diligence. We agreed on valuation and all of that, but I wanted them to do diligence for 6 months before that true full invest. So, so they went through that whole process, checking with the vendors, checking with customers, making sure this is not bullshit, right? Can you actually do this? And they all agreed, yes, makes sense.
Sure.
Well, Jan was one of the first investors in Tesla and SpaceX and a whole series of other companies, electric hydrogen, 12, right? Sustainable aircraft fuel, Joby Aviation, right? Fervo, right? So, so they're not a slouch. They're an incredibly capable company, and he's very well known in the industry, generally speaking. And so, so he sees this, and he's communicated this, that he believes Erthos has the greatest likelihood of enhancing decarbonization of any company in the world, because we have the least cost CapEx in the largest CapEx industry in the world. Solar passed oil and gas last year in total global CapEx.
Right, in terms of
just total dollars expenditures, about 650 billion. And we have the least cost CapEx to do that. And I'm talking the solar part of the equation. Right? The hydrogen part of the equation came after the Series B. The AHAs came after the Series B. So he's just been the beneficiary of that, right? So that's kind of where that money has come from. And we've been doing the Series B until we get to cash flow positive.
I think it's really fascinating to think about, in particular, the Capricorn invested, because in 20-something years, Capricorn's only invested in 43 companies, and you're one of them twice. So 2 of 43. Obviously, there's an incredible amount of belief in you, Jim, and the vision that you have. But what do you believe that Jan sees in the eventuality of the growth, the scale capability? I mean, this is venture capital after all. The alternative that you are displacing is game change in ATI and Nextracker, and embodied in all of that from an ESG perspective is a ton of steel. So can we talk a bit about the decarbonization advantage specifically that Capricorn is investing in, and just talk me through the economics of what you do offset that is beneficial for the decarbonization of the industry? Like, what does that actually mean for the layperson?
So I had a meeting just last week with Jan at his headquarters in New York. There was several other company heads that were in that meeting. In fact, one of your prior colleagues was in that meeting. And I always enjoy sitting in meetings where Jan describes his history. And then he describes what he sees with Erthos. It's fun to listen to. He's a brilliant communicator, and he tells stories really, really well. So it's fascinating. So his roommate in college was Jeff Scull, the founder of eBay. And Jeff Scull made a stupid amount of money in a short amount of time. Jan was off working for Koch Industries, doing mergers and acquisitions. Scull makes all this money when he sells eBay, about $2 billion. And he wasn't into, I'm going to use this money to go do other things. He wanted to give it all away. And Jan was his roommate. And Jan's like, why don't you give it to me? I'll figure out how to give it away, but I'll make money doing it. So that was the impetus behind Capricorn. It was a philanthropic mindset, but make money to do it. To this date, he's been unable to invest at all. Its growth has been so good on the model, the amount that's available to invest, he hasn't been able to invest at all. Even with the ones that he missed, right? Been very successful in the picking the winners, right? So, so with that mindset, it's what can I invest in that has the biggest impact on the world?
Value creation,
the biggest value creation for the world. Recognizing the world has severe issues as we get further and further into this thing. So, so you look at all of Capricorn's investments, they generally have a slant to something like that. DEPCON was a little off. that didn't necessarily have that slant, but DEPCOM gave him knowledge
Right.
about the issues of building solar plants.
Got him into the solar industry.
Oh, well, no. He was already in the solar industry.
Okay.
He bought SolarStar, largest ever project built, right, in the United States. I mean, he was, so he was heavy into solar a while back, so that's his general mindset. How can I invest, have the biggest impact on the world? What are those companies, and how do I support them and get them to grow? And it's not just his money ever. This is try to get multiple companies to put in. If you look at the portfolio that he's got today, Erthos, Fervo, right, using fracking technology and oil and gas technology to unlock the underground heat of the earth to make steam 24/7, and it works. Financially, it's just astonishing what they're doing right now. Just truly amazing.
Yeah.
Right? Electric hydrogen is a good one. There's 12, right? Sustainable aircraft fuel and electrolyzing CO2 into CO, and there's a whole series of processes there. So I've had the luxury of attending some of the LP events and listening to the CEOs and talking to the CEOs myself to understand where they are. So it's really been exceptional.
Yeah.
But his slant is different than your typical VC. It's actually very different because he's done, like I said, that so few companies. It's about 2 a year.
Yeah.
Think about that, 2 a year. That's trivial, right? So they put a heavy focus into each company. Well, so when he thinks about these investments, he's not thinking about return on investment as the first most important thing. He's thinking about, is this fundamental technology, does it surpass first principles to make these things happen, right? We'll figure out how to, the best go-to-market strategy, the right leadership structure. We'll figure out all these things if we need to along the way. But the fundamental technology, does that fly or not, right? Enter SpaceX, Tesla, right? All the different things. So when I introduced this to him, we were 30 minutes. He was hooked. I mean, I'm not kidding you. It was 30 minutes. He was hooked. He understood, put it on the ground.
Yeah.
Are they waterproof? Of course they are. He already knows that.
Yeah.
Temperature, and that was an issue. That was what I had. Yep. And I told him about the temperature. We're done.
Resistance to hail?
Hail resistance to, the glass 10 years ago was hail resistant.
Absolutely.
Right? So go back to all that. So he was there. It didn't take him long at all to get there. And it has to do with this philosophy around the nature of investment. It's very different than your typical VC. So then growth and scale, right? How do you do that? Right? It's not easy to hyperscale companies.
Right.
That's a complex problem. We've been around the horn on this a lot internally to figure this out. Are you the EPC? Are you the developer? Are you the technology provider? Are you licensing companies? Do you joint venture? And it's somewhat of all of the above, right? We look at all these things. So we work. I talk to Jan once a week as an investor. Wow. He's on our board, but I literally talk to him probably once a week. So he's very involved with knowledge and ideas and that, which is fantastic. So when I was describing, I wanted Capricorn to do due diligence on us, deep due diligence, which they did for 6 months to understand the economics and the hows and the whys. In that economics, when you look at all the puts and takes, we remove all the steel. Okay, that's good. You put these things on the ground, that's fine. What's the energy yield? What's the man hours change and cost to construct? What's the land utilization? There's a bunch of variables that come into play. It's a calculus equation, not just a arithmetic equation, right? So the largest needle mover by far is the steel. Right. Approximately 35 tons of steel per megawatt. Wow. We removed that. So there was 25,000 megawatts installed in the United States, 35 tons equivalent. You can, start to run the math. Yeah. Well, all of that steel, you think about the CO2 emissions to make the steel, to transport the steel, right? Is huge impacts to the to the project environmental impacts when you do that.
Right. In terms of the carbon offset.
Just the carbon offsets. It's like astonishing.
It's similar to Ben's business, right? You're dealing in megawatts. It's because you're not buying steel. You're not creating more production.
Right. That's right.
I think we did the math. It was something like 1.5 million tons of carbon per year in the U.S. alone.
It's equivalent in the U.S. consumption of steel in solar last year. It's equivalent to 10% of all the cars emissions, roughly. Yeah. That's crazy. That's just the steel. There's other emissions as well. When you talk about all the labor and the other parts and pieces, there's more to it. But
so that moves the needle on
that
the ESG.
moves the needle, right? The next biggest needle mover, and why it works in the U.S. is the cost of labor. Mm-hmm. So over time,
well, before we touch on labor, running DEPCOM, to the infinite penny, to 4 decimals of the penny, how much each component costs. What is the component stack that's being removed by going to Erthos? Like just the raw cost from a developer's perspective to install it by removing the racking.
Roughly speaking,
just on
the
materials.
Cost of the module, whatever the price of the module is, the balance of materials, module, another 12 cents.
12 cents. Okay.
Approximately.
Yeah, so 12 cents a watt.
Okay. Mm-hmm. But you got to look at the labor component, and that's where it starts to get, the needle moves around all over the place when we're talking about labor.
Because it does require some manual
there's
application
a lot of variables that drive labor, but installing posts in the ground, installing the rack, putting all the bolts on, connecting all the modules, putting a wire harness on, right? There's all these parts and pieces that drive labor. Well, for solar and at DEPCOM, we measured labor, man hours per megawatt.
Right.
Very strict, very consistent, repeatable. You could scale it.
Yeah.
Right.
What's that number?
Yeah. So when I was at DEPCOM, the worst project was 8,500 man hours per megawatt. The best project was 3,200.
Yeah.
It's a pretty significant swing.
Huge swing.
But that man hours per megawatt results in about 20 cents a watt total cost for that man hours per megawatt.
Yeah.
Erthos, now my team might get mad at me if I say these numbers, but I believe when you scale and you achieve the processes and the means and the methods to install everything correctly, that we will break below about between 500 and 700 man hours per megawatt. We'll break below that. So now the 3,200 came in 2018. Or no, 2017. Yeah. Okay, and there's an efficiency component to that, but today you might be at 2,800 or so man hours per megawatt, just depending on the size of the module efficiency. Mm-hmm. But we'll get down to about between 500 and 700. Let's call it a 50. Big picture, it's about 25%. Yeah. If you reasonable average site to site to site. You take all that labor, depending on the cost of labor where you are. Mm-hmm. If you go to India, the labor is really cheap. Yeah. It's not as financially viable. Sure. You go to Australia, in Perth, it's 3 times more expensive for labor in Perth than it is in the United States. Mm-hmm. You go to prevailing wage in the United States, labor price goes up, right? All those have an impact. Mm-hmm. So the cost of labor is a huge effect on this because you've removed all the rack. Right. But not only did you remove all the rack, you cut the land use by less than half. Mm-hmm. It's the same power plant. We use less than half the acreage for the same AC power plant, same energy delivery. Right. Less than half the acreage.
And roughly 30% reduction in cost.
Yeah.
Yeah.
It's crazy.
That's nuts. And 1.5 million tons of carbon per year.
Right.
It was, it's what, 60, it was 35 tons of carbon per megawatt of steel. That number is just
so there's a lot of companies. There's a lot of companies that don't like what we're doing.
Oh yeah,
of course. Tracker companies don't like it. Yeah. I get it. I built a lot of trackers, right? Friends with a lot of the people in a lot of those companies. Yeah. Close friends with a lot of people in those companies. So tracker companies don't like it. EPCs don't like it.
No, because they make their money on labor.
Their money on labor, right? The land is a bit different. They like it because they can get paid more per acre because you use less acreage.
Right, but they use less acreage.
That's good on an environmental case, but it's less acreage.
Right.
So they get paid net less money, even though it's more dollars per acre.
Right.
So steel companies don't like it.
No.
So you've eliminated it. You get into some of the other commodities like inverters. By taking what we've done, we've standardized, right? We standardized the concepts of engineering, standardized the parts and pieces. We've standardized around an inverter. A string inverter, for our application, is a better way to design and build a plant.
Yeah, makes sense.
There's a bunch of reasons why that's the case. So a standard string inverter, 250 kilowatt, 8 of them in a cluster to 2 megawatt with a 2 megawatt transformer, all financially makes sense. You're using a very standard object in a 250 kilowatt string inverter, a very standard object in a 2 megawatt transformer.
So you're going to standardize around, you're going to, oh my goodness. I mean, as we talk about the transformation of the way that EPCs have to think about it, engineering firms, IEs are not going to be big fans of this either. You are going to, as earth-mounted systems increase in percentage of overall market share, you're forcing developers away from central inverters. You're forcing developers away from huge steel infrastructure. Vermeer is not going to like this.
Vermeer won't like it. Right. That's right.
Yeah.
That's right.
Pile driving companies generally.
So there's a lot of headwinds against us.
Yeah.
Right. But who is the winner aside from Erthos? The developer. And the developer controls the project 100%. His margin. Their margin. I mean, I know by fact because we're doing deals right now. 4x. Yeah. On some deals, 4x in the return on a dev fee. Right. 4x. 2x is kind of a sweet spot. You can reduce the PPA price. Right. But if I've got a fixed price PPA that based on a tracker, and it was bid 2.5 years ago, and now the prices of stuff have gone back up rather than down. And now those projects are either underwater or close to underwater. They got to go back in and renegotiate. They can use Erthos instead. Yeah. Right. And they can make more total dollars, the developer can. Yeah. So by having the developer be in control, that pulls against those other forces. Right. But here's the problem. Those developers, in order for them to be efficient, they've often partnered with a few of these companies. Yeah. They'll form long-term relationships with certain supply chain, whether it's a module or a rack or an EPC. Right. They'll form those long-term relationships, especially on the large-scale projects. Yeah. And I was one. I had those, I understand it. For sure. And so there'll be a resistance to that. However, there's one number that trumps every single time, and it's the price per kilowatt hour. It always pushes down. It will always win. Yeah, the LCOE. And if that developer doesn't bend, they will lose their next PPA bid against another guy who's bidding 5% below them. Yeah, it's inevitable. That's why. I mean, that
market pressure is the reason that developers started using trackers.
It's why they started using trackers from the outset. Yeah. So it's fascinating if you look at the evolution of these companies, be it for solar or any of the module technologies, but then you certainly move into the racking technologies.
The fundamental question is, how do we drive LCOE down, which you've been able to address. On the solar side, I'm now convinced. I understand why Charles and Daniel and so many others that I respect have not only invested in, but are now proselytizing this technology. I want to go back to the epiphany moment where you started to realize that this could have a bigger impact than just revolutionizing the way the solar is deployed and getting us the lower cost electron. If we have free solar, if we had lowest cost electron, then what does it enable? It enables this hydrogen economy that has been struggling for 50 years plus, for 100 years. Great. I love the way you walked me through replacing steam creation. That value creation process makes sense to me. It's a niche application that's not so niche. 12 gigawatts in California alone would satisfy most companies.
Here's a number. This is an important number. If you take all the hydrogen in the gas and ammonia, if you take the energy content of that, you look at the total energy consumption in the United States, that is 3%. Okay, all hydrogen is 3% of all energy for those two markets.
Sure.
Steam is 30%.
Of all energy?
Yeah. Steam is 10 times bigger than if it was just pure hydrogen. Now, these markets are so large that it's hard to wrap your brain around the magnitude of what we're describing.
Yeah. Are we talking just in the U.S. or globally?
That's just the U.S.
Okay.
Just the U.S. So it's hard to appreciate these points.
So one of the values of hydrogen.
And by the way, where does that come from? People think about electricity when they think about solar.
Right.
The grid is only 17% of all energy in our country.
Right.
The electric grid, 17%. All electricity makes up 17% of total energy consumption.
Wow.
What's the rest? Well, gasoline's one. It's about 35% or so. Yeah. Industrial energy consumption in the form of steam and heat.
Yeah, industrial heat.
It's huge. Yeah. It's a huge number.
Yeah.
Making food.
Yeah.
Melting things.
I mean, this is most of GE's current business, right? Combined cycle plants.
Right. And people can't, unless you're in it, you've been in it, you don't know.
I understand the steam part, and it's gigantic. But even that pales in comparison to the capacities that I imagine folks are going to start to idealize when they realize, like, we've got a new way to create hydrogen at basically free electron scale. Where does it lead you? And in particular, something that stands out for me is a sector of the market that I never would have expected to see Erthos dabbling in, because it has been owned by, let's call it like China, for well over a decade. You made an announcement 7-8 months ago, Navajo Poly, which I presume through the announcements that I've been able to glean is about bringing back to domestic shores polysilicon production. Well, I seem to intuit like, okay, Jim's in the solar industry and we've got this domestic manufacturing push, but I don't quite get it.
What's the leap? So you've got if you go back and you think about the hydrogen piece, developing that hydrogen piece, and I was predominantly thinking about California. I mean, honestly, that's what I was doing right in that market. Now I was thinking about hydrogen in the Texas market and making gasoline and fuel and all. So those two markets were definitely where my brain was. I also have a home that I have in Colorado, and I was driving back and forth between Phoenix and Telluride, and I was doing it fairly regular. And there's only one good drive spot, and it's across the Navajo Nation. It's about 5 hours of drive time through the nation to get between the two. It's about a 9-hour drive. 5 hours is through the nation. So you're making that drive, it's amazingly beautiful. Yeah. I mean, it really is. This desert Southwest is just, the Monument Valley, and it's a lot of time to think. And every time I drive through it, it's like, why is there not solar here?
Right.
It's the best solar resource, second best solar resource in the world, behind the Atacama Desert, but certainly the best in the United States. Yeah. You have all the additional tax credit benefits from being on a tribal land. Navajo are the largest tribe in the country by far.
Right.
It's 27,000 square miles of land. Total solar built on Navajo land. Total 130 megawatts.
Wow. That's a
what?
Infinitely small number.
What? Why? That's strange.
130 megawatts.
Yes. 3 plants total. So it's not that I knew that, but it was like, something's got to be done. Yeah. So right about that same time, one of our guys, 2 sons play football together. His name's Arish Malimi. Arish is half Navajo, but he's the general counsel for NTUA, the Navajo Tribal Utility Authority. They do all the electricity grid for Navajo land. And he's their general counsel. He is friends with our general counsel. Sons play football together. Introduction between him and me. I'm like driving back. So I was like, well, let's have this conversation. Yeah. After those introductions, and and I'm driving back and forth, like, how do we do this? We have to figure something out. We have to figure something out. And after I've gone and met with the local folks, you learn something about why there's only 130 megawatts. What's going on with the local tribes? Land is very complex within the Navajo Nation. It's not as complex in some of these other tribes, but it is within their tribe.
Sacred.
You can equate it to, so you live in North Carolina. Imagine if the state of North Carolina owned all the land in North Carolina and you had to lease the land to build your house. That's the Navajo Nation.
Yeah,
that's how it works.
I understand it. That's how it is in parts of Mexico.
And then you get to the community, the county level in your state. You say, okay, if you want to build something in that county, you have to get approval by the county supervisors who are elected. And it's just the supervisors, you got to get approval. In the Navajo Nation, they have counties, they're called chapters. There's 111 of them. But the approval has to be a unanimous consent from at least 25 people that live in that community.
Wow.
And they all got to show up to have the meeting to get the consent. That's extremely difficult to do. There's 550 souls that live in the Nanazad tribe or chapter. 25 of them got to show up, and you've got to get them to vote unanimously to build your project. Well, that doesn't just happen. That's tough to get. What do those people want? It's not the land use. There's a 30% unemployment. They want jobs. If you build a solar plant, you got jobs while you build the plant. Fine. Well, what about after that? There's no more
Small
revenue.
fraction. Small fraction of jobs.
Build manufacturing, different game. Totally different game. So driving across back and forth.
That's also why the casino makes sense. Not only does it generate revenue, but it employs people.
It employs people. So the as I'm driving back and forth, is how do we get manufacturing jobs on the Navajo Nation? And not just build solar plants. So that was the starting impetus behind that idea.
Part one.
Part one of where this is coming from. So I'm going to hold on that idea for a moment and shift over to back to the hydrogen for a moment, because there's an interesting thing that happens with hydrogen when you burn it. It burns at about twice the temperature of natural gas. It's really hot. It'll melt anything, pretty much anything. It'll certainly melt glass and steel and all those things. So as I'm researching uses for the hydrogen and oxygen on the Navajo Nation, if I build a project and, solar to hydrogen and the uses, well, I can make ammonia, I can make, but I can also melt stuff. Well, there's another fascinating magic trick to do with efficiency. Most of the materials that get melted in the world get melted with an electric arc, called a submerged arc furnace. Submerged arc furnaces for melting steel, for melting glass, for melting polysilicon, it is one of the industrial type of machinery. So, but submerged arc furnaces need an electric arc. They need electricity to do the work. Why? Because an electric arc is really hot. It melts all the stuff. So if you say, well, where is the cheapest electric arc or electricity? It's absolutely in China. And it's absolutely in one type of electric generation in China, in their dams. It's their hydro, just like it is in the US. 24/7, cheapest form of energy in the US is hydro. So I'm researching the problem of energy to make these various materials. Well, polysilicon is quartzite. That's the raw material, polysilicon. You start there, you go through a series of processes. But the cost of polysilicon in a solar panel today, about half the cost to make the polysilicon is the cost of electricity. About half.
Okay.
And the cost of the cell, this polysilicon cell, it's not quite half, but it's a significant portion of the cost of the panel itself.
Yeah.
Right?
The ingot is.
The ingot.
Yeah.
And then the cell that goes, So, okay. Well, since China has these dams, the United States' largest dam is Grand Coulee at about 6 odd gigawatts.
Yeah.
Hoover's about 4. Yeah. You put all the dams in the United States together, all of them combined, it's about 17 and a half gigawatts.
Right.
China built the Yangtze Dam on 3 rivers. That's 22 gigawatts. Single dam.
Yeah. Bigger than everything we have.
Everything combined in the U.S.
Yeah.
Now they flooded 50 million people to do it. That's environmental, whatever. Mm-hmm. They have 220 gigawatts of hydro in China.
That's staggering.
That's staggering. And that's the cheapest form of energy. Yeah. So why are they making stuff cheaper than us? Is it because they're using coal? Well, okay, coal's cheap, I get it.
Right.
But hydro is cheaper.
Right.
So if you use the hydro, pump that into a submerged arc furnace, melt the stuff, you can make the cheapest melt things that you got to melt in that form.
Silicon being one of them.
Silicon being one of them. So then you start researching, well, where does all the silicon come from? Well, in the United States, silicon was, if you go back to the existence of silicon at all, computer chips, that's where it all started, Silicon Valley, right? Computer chips. Circa 2010, 2011, right in that window, the consumption of silicon, 50% of silicon became solar-based versus computer chip-based between 2010 and 2011. Just because of the volume of silicon consumption. Right. And while the silicon for computer chips is higher purity versus the solar, just the raw volume, you still got to melt it, you still got to process it to the various grades. So that raw volume shifted. The price of solar panels came down as soon as the tipping point of silicon went to more in a solar panel than was in a computer chip. Right. It's based on the price of a panel, based on the price of electricity, rather than the price of a computer chip.
Right.
So, so China sees this, future step and says, well, if I use all of this low-cost electricity to make the polysilicon, I can make a lot of it here. They were already making polysilicon in China, with computer chips. The U.S. still makes computer chips here, right? The high-tech stuff. But the volume is tiny comparatively to solar, right?
And at this time, by the way, there were silicon plants in the United States. Hemlock had one in Tennessee.
Wacker.
REC had one in Norway.
They're in the Northwest. Where the dams
Washington,
are. They're in Washington, right? They're in Tennessee because of the nuclear. So wherever there were the dams and the nuclear, that's where those plants were, right?
Creating silicon.
Now, but where does the raw material come from? It's kind of crazy. The majority of the solar silicon raw material, quartzite, comes from North Carolina.
Spruce pine.
What? Well, it turns out there were some silicon plants or quartzite mines in New Mexico, right? So, Wacker and Hemlock, they had facility in New Mexico. So it's kind of distributed, but the quartzite in North Carolina is high quality quartzite. They dig it out of the ground there, ship it to China, they process it, and then we ship it back in the form of finished, cells. So the interconnectedness of all the supply chain is incredible, right? But it's the price of electricity that drives that. And so
rather than the price of computers.
That's correct. So now, if I take the whole idea of a submerged arc furnace and I say, well, I don't need an electric arc to melt the stuff because I can melt it with a flame, right? If you don't have to convert the flame to electricity in the first place, the way we make electricity in the U.S., dominant, is burn natural gas, make a flame, turn a turbine, make electricity. If I don't have to convert the flame to electricity, about 65% of the energy is lost in that conversion. If I never have to do that, if I just make the flame and I heat the material right there, you get all that energy back. So big, long, complicated math equation to get there, okay? But if you include the US's IRA for hydrogen, $3 a kilogram and the other incentives, you can ultimately make hydrogen cheap enough to burn with the oxygen to melt the polysilicon here in the US, where the cost of energy in the flame form is significantly less expensive than the cost of energy coming out of the dam in China. Significantly lower.
So you invert the model.
Right? The raw material is already here, quartzite. I don't have to ship it all the way to China. I can just, So there is absolutely a model where you can make the poly cheaper here than you can from China. The poly, the ingot. So you got to get the quartzite, to the processes to get it to the beads, to the solar grade polysilicon, and the Schottky process to draw the ingots. All those processes all take heat, remove the electric form and go to hydrogen combustion, regain all that energy content. Now, all of those technologies got to be developed. Okay, it's not easy to go develop those; they haven't been done yet. But the processes, the fundamental ideas and technology, that set of ideas, financially it works. These are first principles. This is no different than the battery-powered Tesla. The first principle worked. The battery in that computer, if you stack them up and make a battery for a car, it works financially. This is why the Tesla, now the cost of the cars and the batteries have come around. Same thing is true with these first principles. Now, it starts with the IRA. You can't do all this if you don't have these incentives. But we must solve the hydrogen problem. Because if we don't, China is making solar panels right now for sale in other countries for 8 cents a watt. I'm buying them in a project in Australia. I know that's the price. You take an 8-penny module, DC, directly on the dirt, and you put it into a very inexpensive electrolyzer, and you make hydrogen, and then you can take it and use the sustainable aircraft fuel, the other process. You make a hydrocarbon that's transportable to the rest of the world. China can displace. The U.S. has a hold on energy because we have a huge amount of natural gas. We have our good oil reserves, but we have a lot of natural gas. U.S. #1, Russia's #2, right? You look through all the energy countries in the world, China's in there, but China's using their hydro to get control over solar, and solar is now the cheapest, period. Convert that into hydrogen, you have a very serious strategic problem if you don't start making the stuff in this country. So Navajo Poly takes all the benefits, takes the IRA, big benefits, I'm not going to deny it does, beautiful sunshine, improves the lives of all these people because you can manufacture, land, amazing quantities of land, that's generally unused today. One of the components of land is the coal mines, reuse the old coal mines, that land, we're actually looking at that. So it's a big picture. It's a big vision. It's an audacious vision. But if you're going to solve these big problems, you got to put all of them together. It's not just one piece, one part, this company, that company, and it's got to bringing them all together. So, and then you got to get it financed, right? Well, you got to bring the economics to the street.
Well, it's interesting you mentioned financing, right? So at the end of the day, this is about bringing the economics to the street. We've had a successful run as an industry of getting public market acceptance finally of this asset class. We've mentioned three of them here: ATI, Shoals, Nextracker, three of the darlings of our industry that have gone public.
Amen.
Where do you see Erthos in the next 3 to 5 years? I mean, is it destined for a public market?
Yeah.
It seems like to be able to build a polysilicon plant, you can't do it from
scale
venture
to the
capital.
magnitude I'm trying to. Well, you could with VC. It's amazing what VC is doing with one of our sister companies. I say sister company is Redwood Materials. Multiple billions into that plant so far, all still with VC.
Wow.
Right. So it can be done. Okay. But
and obviously SpaceX is not a public company.
Right. Exactly. So so it can be done, but at the end of the day, the companies what we're talking about has global implications. It's directly competing with fossil fuel, trying to displace fossil fuel, specifically natural gas. Right. Being focused on natural gas as the key fossil fuel to displace in the beginning of it, ultimately creating renewable hydrocarbons. But people often say, "Oh, the oil and gas industry is not going to like you." That's not true. The oil and gas industry is still going to be deeply involved in transportation.
And they understand molecules.
And distribution of these molecules. You can't get away from having a portable fuel.
Right.
Right? Now, some people go, well, the batteries are going to win the day. Batteries don't make energy. They're not the source of the energy. You have to create a source of energy.
Yeah.
That's the problem, is the source of the energy. The sun is the source, inputting source.
Right.
But then by putting it into the water, ultimately making the hydrogen, putting it into a hydrocarbon, you have to make that portable fuel as a long-term process. Batteries have their place, no doubt. Yeah. I mean, no doubt about it. Yeah. I've got a Tesla. I think it's the best car ever, without a doubt. So the, battery recycling is going to have its place within all of this, no question. But to think that we're going to take and we're going to electrify our way out of the carbon issue is a fool's errand, in my opinion. Only 17% of the energy in the country is electricity. You would have to quintuple the grid. The grid's already the constraint. Right. And you have to make it 5 times bigger, and it's already the constraint. You got to get off grid. You got to localize these consumptions. And so by doing this, solar to hydrogen, and frankly, solar to battery as well, because that's a transitionary one. For sure. Putting data centers, right? Consuming 24/7 energy, off-grid data centers. The rate of rise, the rate of growth and addition, we have to separate ourselves from the grid. Yeah. And it's not that the grid's bad, the grid's good. You just have to go faster.
Yeah, we don't have we can't scale that infrastructure.
We can't scale that fast enough.
Right.
And we have to scale it faster.
The cool thing is, this already happened 100 years ago.
Yeah.
This is how the grid became what it is.
Exactly.
The grid will catch up. It's inevitable. But we have to actually create generation assets faster than the grid can scale. Yeah. Are you concerned at all that your technology approach challenges the conventional wisdom that would suggest that Trump is very pro oil and gas, pro natural gas in particular, and our natural gas resources, right? It seems that you would be offsetting or diminishing the capacity for exploiting all that natural gas.
The demand for energy is well beyond where we're able to create it from solar or wind or hydro.
Yeah, especially with AI.
Especially with AI. It's growing much faster than we can supply. So I actually believe just politically, there's an interesting possibility where you tie drill baby drill with the IRA. Use one to the other. The United States must use its natural resources to get in front of the competition. Right. The number one resource we have is natural gas to do that. The number one they have is hydro.
Hydro.
Okay. Between the two of them, you've got to solve the hydrogen one. In the meantime, you got to put the battery component in it, And both are doing a lot of batteries. They're making them, we're consuming them, right? There's a lot of both ways. But if you took in the U.S. and you said, all right, for every gigawatt we install of solar, wind, battery, whatever, you also are able to drill new wells, right? And you tie the two. You take some of the taxation on the natural gas, and you use that to help subsidize these other sides. So you connect these two things together. You remove the whole my
Us
side,
versus
your
them,
side,
right.
us versus them, and you bring them together as a unified method. I think that's like one of the most powerful things we could do as a country.
Fascinating.
Personally, I don't think they'll. I think the U.S. content component of the IRA, Trump is obviously a major fan of U.S. manufacturing. U.S. content will drive that. He's a fan of tariffs. Rise tariffs, rise U.S. content percentage. He may just do that.
Right.
But if you do that, that increases manufacturing in the U.S. and increases. So it's okay to do that, but you can't increase tariffs and remove some of the tax implications. That screws things, right? That goes the wrong direction. Now, as you can, I don't care about people's political viewpoints around this person, that person. Trump is a very logical, methodical businessman, and energy rules the world. He's putting the right people in play to return U.S. dominance in energy.
Yeah.
We already have dominance in natural gas.
Makes sense.
But you further increase our dominance in natural gas. You're going to help alleviate some of the tax issues and more revenue for the country, and so on and so forth. So I think I don't think he's going to hurt the renewable industry at the end of the day. I think whatever happens, the policies that he comes and his team comes up with will ultimately enhance the renewable space. You don't put Elon in the middle of this, who is a major fan of solar and a major fan of electrification of the batteries. That's not by chance.
Yeah. Jim, you, by any metric, have had a successful career. Most people would be very happy by the time they're in their 50s, early 60s to have achieved all that you've achieved economically, as well as just from a pedigree and an impact perspective. You've installed gigawatts, many of them first projects in nations. Many of your friends are, in fact, retired from First Solar and other companies, even from Depcom. You've helped retire friends from the need to work. Yet here you are with an audacious vision that minimum is going to require 5 to 10 more years of your working life to bring to fruition. What drives you?
When you find a passion, right? You say your passion, you don't work a day in your life. Once you find the thing you're passionate about. In all of my career, I enjoyed what I've done all the way through, but it was never a passion. It never turned into a passion. When this idea first hit me, it's like, oh, this is meaningful. This thing moves the needle and affects the world. No question. It affects the world. I've already had some level of effect on the world in what I've done, but the effect this has is no doubt. So it's really easy to get up in the morning just because of that alone. Okay.
It's hard to go to sleep.
When he sold the last company, we sold Depcom to Coke, made enough money, go retire.
Yeah.
And I did.
Yeah.
And I got bored. I mean, like really bored.
Yeah.
Couldn't. So when this idea hit, and it was like, that's it. And, it kind of expands out from that. 2 months in, company founded the company on my 50th birthday, right? Literally 50th birthday. That was the day of took my family over to Europe for a 21-day family vacation to Europe. It was awesome. Get back, get off the plane at midnight, get up and ride my bike the next morning about 5:30 in the morning. About a half an hour into the ride, had a full-blown heart attack. All the way. Gonna die. And it was moving, to say the least. I was about 300 yards from the road. And I mean, like, I know it's happening.
Yeah.
And I was off the bike. I got back on the bike, rode 300 yards, and fell down in the road. And this woman drives up, picks me up, gets me in her car, drives me to the hospital. Couldn't pick her out of a lineup to this day. Don't know her name. Wow. 2 months after I started the company. I'm pretty sure I was meant to live.
Yeah.
I'm pretty sure I was meant to live. So that creates a passion, right? Yeah. I started to see things in a different way. Started to recognize some of my own history, the experiences I had. The whole hydrogen thing tied me back to relationships from 30 years ago, bringing things full circle. One of the young men that works for me, Cody, I was his coach when he was 10 years old in baseball, right? He is definitely one of the top guys in the company, no question, right? He'll probably be a CEO one day. I don't know, but you start to see other parts of your life, right? So then fast forward up into this discussion with the Navajo, and I've had this conversation there in front of dozens and dozens of people, multiple times, and that in the process of that conversation, I told them, I don't have to do this.
Yeah.
I can go do this someplace else, right? I'm doing this because I think this is the right thing to do, and this is the right place to do it. And the return to the people that live there, the local people have been frankly abused in so many ways. And I believe it's wrong. And I think there's good things to come for, these groups of people. And so it's like, well, why do you do that? Because it's a good. It really fills you up. Yeah. So last week I was there and introduced some more people. It was really fascinating. We get done with this and we went to dinner later that night. And several of them looked at me and they go, I've never felt energy like that in my life, ever.
Emanating
from the room of people.
Right.
And the positive, and I think it's love. I think that's the strength of that energy is love, right? But these are, one of them was a big banker, right? His whole life being a banker, and hardcore banker. And he was like in tears almost, expressing this gratitude to me. Yeah. Right? And go ahead.
I recently learned something that I think is fitting here. I was sharing it with Jeremy just yesterday that there are experiments being done to try and prove the law of attraction, right? Which supposes that we can through intention, impact the world around us. Effectively, we are all energy and therefore we radiate frequency.
Yes.
And so they've put people into this, I wish I could remember the name of the box that would make this story more meaningful in that sense, or more credible. But effectively, they put you into this container that has a name where there are no frequencies that can come in so that they can actually measure the frequencies coming out of the box. Do you know, they discovered the highest frequency that emanates from humanity. And you'd probably think that it's love, right? Because you said, I believe that it was love. I think that what I learned from, at least from this video, is something else that I think ties back to this banker and why someone would say, I've never felt that before. It turns out that the frequency we emanate that is 4 times stronger than that of love is authenticity. And lo and behold, when you get a banker that kind of sees the world through a different lens and can have an authentic expression that doesn't feel financially driven, perhaps, feels like it is driven from a place that's a higher order.
Yeah,
I would posit that what was being felt in that room is genuine authenticity. Yeah. I want to bring this as something that you told me about in a meal that we had recently. I want to tie it back to sort of building a culture in a company, because you've learned a lot. Yeah. You've worked with some of the most powerful CEOs in our industry, publicly traded companies. Could you talk about leadership as a principle that you've learned from what is arguably the best volleyball coach in the world, Marv Dunphy?
That's an interesting one. So I'll start it out by go to the whole concept of authenticity.
Yeah.
So where do I come from? I was born and raised in a small town in Northern California called East Nicholas. Grew up on a river. You could go 20 miles either direction, never see a soul. I was the quintessential Huckleberry Finn.
Yeah.
That's how I grew up. 100%. That's how I grew up. Went off to college at Chico State University, got a degree in mechanical engineering, and then started traveling the world. Yeah. And, I've been to 35 countries in my career. I've just seen a lot of culture, a lot of places. And then been sold big projects, multi-billion-dollar negotiations with 200 lawyers, and I've been all these things. Being authentic is it's a must. I just am. Some of my prior bosses tried to change me. They wanted me to dress a certain way or talk a certain way or don't cuss. I tend to cuss. I haven't cussed very much. I'm actually kind of proud of myself. I hadn't cussed that much in this, but
I'll just note that you're one of the few people I'm around who drops more F-bombs than me. So it's refreshing.
So you just, by being authentic, it's really easy for other people to see through people who are inauthentic.
Yeah.
So if you just are that way, it doesn't matter what you do, how you do, just be that way and let the good things come from that, no matter what, right? Doesn't matter your political persuasion or your this or it's just be authentic, right? So I've kind of like run my life that way. I live by 3 important premises: trust, respect, and integrity. Those are the 3 big, character traits that I try to, but being authentic just kind of like ties everything together. Go back, my oldest son is a volleyball player, very good volleyball player, and had an opportunity. He actually got, he was a walk-on at UC San Diego, UC San Diego and Pepperdine. He got walk-on. Both coaches said yes, and he was accepted by both schools. And he said, "Dad, I want to go to Pepperdine." And I'm like, "You're not going to play, ever."
Why? Explain why.
Because it's the equivalent of Alabama in football to volleyball, right? Yeah. And the reason for that is for 40 odd years, their coach, Marv Dunphy, was, he's the winningest coach in volleyball history and all of volleyball, but he was the U.S. men's volleyball team gold medal Olympic four-time winner. Karsh Karai, the greatest volleyball player in history, he was his coach, right? So he was the head coach at Pepperdine for all those years, 30-something years. Mason's first year, Marv was the head coach just during his first year. In 5 years of Mason playing volleyball, he saw the floor one time. one time in 5 years. And I had told him before he ever went, I said, you'll probably get to play at UC San Diego. He says, Dad, I know I'd probably get to play, but I want to play for the best team.
Right.
Because I'd rather sit the bench on the best team and experience what the best team is about and what does it take to have a winning culture, right? Then, UC, nothing wrong with UC San Diego. But they just, they're not in the echelon.
Nobody there's watching the podcast. You can talk about them.
So we went along and, 5 years, and he saw the floor one time in 5 years. Luckily, I was there the day he did it. Marv put him in because my wife and I were there.
Wow.
He saw we were there, and he calls him off the bench and puts him in for one serve. And he serves it long.
So nervous.
He was so nervous. And he comes back, and Marv's like, it's all right. It's your parents are here. Don't screw it up. Right. Anyway, so fast forward into his senior year at senior night, and I was just going up to him to thank him for, the experience that I watched him coach. Because, in Mason's freshman year, one of the things that he gave to all the kids was this shirt that said gratitude on it.
Yeah.
And so his model, it wasn't just teaching the kids. He coached this way. He lived through gratitude. He led through gratitude. And I watched it firsthand. And I watched these players turn into men, but really all of them amazingly good humans. And so by his time Mason was done, I was just so impressed with Marv. He was an emeritus coach. And so I walked up to him after and just shaking his hand saying, thank you. And he looks at me and then he's talking with this other gentleman, and he says, and I didn't know the other gentleman. And he looks at him and he says, who's your favorite player, your favorite athlete at Pepperdine in all the sports? The guy, he was thinking for a moment. He said, Mason Tyler. And I was just like, what?
Blown away.
Your favorite athlete?
Yeah, in the school.
He's seen the floor one time.
Yeah.
In 5 years of playing. And I looked back at Marv and he grinned. And then he said, he asked the guy, why is that? He says, he's the best teammate, period. He supports everyone on the team and is grateful for being here, is grateful to be within this program, to learn what life is about, right? And that was definitely Marv's doing. Right? So we get done, and he said, and then Marv says to me, he says, do you know who this is? Oh, no. He says, Mr. Potts, it's our athletic director.
Wow.
I was blown away, totally blown away. So over the course of this time, because I saw him and I would watch, I actually used gratitude, leading with gratitude I changed my method of leadership to project that and understand that you don't do this shit alone.
Yeah.
You just don't. You get, especially, you have a heart attack and you're dying and you know it, you feel it. It changes your perception on, the way you look at the world, and it gains a much greater appreciation for the people around you and what they do. Not everybody makes it within startup companies. There's lots of complexities. There's puts and takes. Always be respectful in communications, but be grateful for what you've got. You're not the only one who did it, not even close. You got to be grateful for the people around you, and guys like Jan, right? Yeah. I couldn't have done this without him, no question.
Yeah.
You think about a relationship with the person who's providing the money. Sometimes things aren't going exactly right, and they've got a hold of you, and you're stuck, right? And he's never ever done anything to show that type of behavior ever.
Wow.
He operates in the same way. That gratitude, he's grateful. As wealthy as he is all the stuff that he's done, he operates in the same way. And, you can start to see it and you feel it in the energy of people. So that's what I think I was feeling at the Navajo. That's what I think they were feeling. That authenticity and that it's all connected. It's all connected. And, the older I get, the more I begin to see that stuff and recognize the values behind it, and it's not touchy feely. It's not, I'm a man, I hunt and fish and I'm all that stuff, but it's powerful. It's powerful. It's motivating too,
Are there any particular books that have made an indelible impact in the way that you see the world or the way that you lead or the way that you think about life, philosophy, et cetera? Yeah. One way to think about it is, what books have you read more than once? What books do you gift to others?
So there's books on business that have been quite beneficial. Patrick Lencioni is a fairly famous, I suppose, author within business and
fables. Teaches through fables.
So there's a single book that he has. It's called The Ideal Team Player. And I've read that book a dozen times. Wow. And I've tried to implement those ideas of, hungry, humble, and smart. I try to implement it myself and see it in other people, actively pursue looking at that and use that as the basis for finding good talent and hiring. Make sure you have all three traits.
Hungry, humble, and smart.
And then if you find that you've brought somebody into the organizations that's not one of those three, or they've lost one of those three traits, because you do.
Yeah.
You sometimes, like hunger, sometimes you lose that. You lose the interest and desire and hunger to learn or do or
Most
whatever.
people retire because they've lost hunger.
So, it's good to remove that from an organization. So you try to keep those three traits. So that one's a powerful, as far as business, right? Just the raw business of people. I love world history, the history of the world and the old ancient history. Sure. So I listen to the, why does the earth, where did humans come from? The history of the human population 12,000 years ago to today, and how has information come about in all the different ways. So the different cultures, different major cultures of society. So I like all of those types of things. But I say predominantly, I'm a scientist-minded person, and I'm an inventor. My passion is inventing. I've got dozens and dozens of inventions, and if I ever, finish through Erthos and get this thing going, and I want to go, I've got more inventions of things I want to do.
Yeah,
right.
You're a modern day Thomas Edison,
and I love it. I absolutely love it. I'm building my shop to go have all this stuff and have people that'll go do all that. So I fill myself up with knowledge around technology. Even though I try to simplify often technology, I've learned a lot, as much as I can about technology, and so most of the information I read are about stuff like that. But people and culture and history, I love that as well.
Have you cultivated a particular habit or ritual that gives you leverage in your life?
Okay, so I'm a procrastinator.
Really?
A horrible procrastinator.
Well, please talk to the rest of us about how you manage it.
Yeah. So oddly, I work very well under pressure.
Yeah. Well,
that's when I do my best stuff.
Most procrastinators
I'm most
are
inventive and creative under pressure. I'm quite calm under pressure. So it's almost like I force myself into that situation in order to get the best out of myself.
Yeah.
Oddly.
Like psychosomatic, that works.
Yeah, maybe. And that started early on when I was in college. Test is coming up tomorrow. All-nighter, a can of Coke and a pound bag of M&Ms, and then I'd sit at the desk and do the same thing while I'm taking the test.
Yeah. Right? Oh yeah, priming. Yeah.
So I when the intensity rises, I often don't sleep. I'll do an all-nighter every 2 weeks, every 2.5, maybe 3 weeks.
Wow.
I'll do an all-nighter just naturally. Maybe every 2 or 3 months, maybe every 6 months, I'll do 2 of those in a row. Oddly.
72 hours of no sleep.
Yes. Wow. Done that my whole life. Strangely. But then
What are you
I'm
doing
on the
at-
other
at
side
3
of
in the
that.
morning?
On the other side of that, I'll sleep. I've slept 24 hours straight before too.
Right.
It's just so my body finds its energy.
Sure.
I used to travel all over the world.
Yeah.
I was into Asia and I never found a standard sleep pattern. So
Are there any particular tricks that you found to help get you over the procrastination hump? Because eventually you do have to start.
the procrastination up, I'll come to that. But
Yeah, sure.
to try to answer the one other, there is one thing that I found. Your body knows when it needs to wake up and it knows when it needs to go to sleep.
Yeah.
Let it tell you when to do that.
Sure.
If I haven't ever been able to find myself do a pattern, go to sleep now, get up now,
Okay.
and set myself into a pattern.
Sure.
I find it's best if I let myself wake up when it's time to wake up, and I'll let myself go to sleep when it's time to go to sleep.
So I woke up at 3:30 in the morning. I should have just gotten out of bed.
That's what I do.
Right.
If I wake up at 10 a.m., then I get up at 10 a.m.
Right.
Now, I'll set alarms and stuff like that. If I've got critical meetings that I'm trying to do, then that's a different story. I got to do that.
You got to get back to the airport.
But I try not to intentionally schedule meetings before 10 a.m. to allow myself, if I sleep, then I sleep. If I don't, then I don't.
We're peas in a
But
pod, Jim.
who knows
Tyler.
what, right? So
Everybody that has been worked with me for the last 5 years knows Nico doesn't like meetings before 10.
right.
I actually learned that from the CEO of Timbuktu, the bag company.
Yeah.
And he would bike in from across the bay to San Francisco.
Yeah.
And to do that, he would either have to leave at 5 or 6 in the morning, or he would have to force the rest of the work world to work around him. And so he would just bike in, take a shower, 10 o'clock meeting. I love that.
And then I go to sleep when I'm tired.
Yeah. So often that
If
can
I'm
be
not
7.
tired, it could be 7, and I'll fall asleep on the couch and I'm out.
Yeah.
But it's often after midnight.
Do you know the gift?
And I'm watching. That's when I do the YouTube.
Yeah, of
And
course.
that's where I'm learning
Yeah.
and thinking and
Yeah.
all of that.
Jim, I know I could spend hours with you, and I really am grateful for the time that you've given us. This is one of those episodes that I just knew I wanted to kick off 2025 with this conversation, especially because it challenges the way we think about our infrastructure. It challenges the way we think about installing solar, or the way, what is hydrogen useful for? So I have a couple of questions that I like to end with. The first is, if you could have every person that you encounter, that you meet, leave with one thing, right? If you could leave them with one thing, what would that be?
We've solved the world's fossil fuel problem.
Amazing.
We have. No question.
I feel like
And
you're,
it's not bullshit.
yeah,
That's 100%. 3 months ago, I sent a photograph of my whiteboard to my father
yeah,
because it was the problem that we've been working on for 25 years.
yeah. I must feel
And I
wonderful.
sent him a picture and I said, we've done it,
Yeah,
right? And it's not just optimism.
right.
I know we've done it. And now it's push through and have the grit to get to the other side.
So what I hear in that is every person that meets you, you want them to leave with a confidence and a belief that we have solved this problem.
the world is going to get better, not worse in this piece of the puzzle. This piece of the world is going to get better.
Yeah. And as a result, what will have changed as a result of the work that you are doing?
Yeah. The beauty of the sun and that form of energy is everybody has it.
Yeah. It's equal access.
Geopolitically, there's 9, 10 countries. I think there's 19 countries total that have oil and gas under their land.
Yeah.
But 9 or so of them have the control around those resources.
Right. Water is obviously geographically controlled.
And solar to hydrogen, and that unlocks everyone's energy. It unlocks everyone's. So it changes the nature of the geopolitical landscape. Now, you still have to do some other things, and there's still banking and finance and all these other things. So it's not like these countries are going to geopolitically.
Yeah. It doesn't create universal equality.
But it creates a sense of self-reliance, right? On, where you are. And I think that is, that's a meaningful thing.
Yeah.
I don't know the impact. Who knows where it's going to go? But I think that's a beneficial thing for the planet.
I love it. And it's an audacious vision, one that I am not surprised to hear.
Yeah.
coming from someone who has challenged the very industry that made him. And I love it. Jim Tyler, thank you so much for giving us access, for sharing the vision and challenging all of us to think different about the work that we're doing. There is hope that we are.
Well, keep doing the work you're doing, communicating this stuff to the world. That's also a passion.
Yeah.
It has to be.
Mm-hmm.
And there's a lot of it.
Yeah.
And keep going on those different people. Don't just keep drilling in to find those people. There's a lot of good ones out there. No question about it.
Yeah.
I know I'll give you my list of folks that I think you should talk to, and I know they'll be excited to do it.
I can't wait.
Yeah.
Well, in the meantime, we'll be here each and every week, as we always do, capturing the stories of the visionaries on the front lines of the clean energy transition. Thank you.
Thanks to you.
I also want to thank you for tuning in. It is because of you and the trade that you make of your time for this knowledge that we get the privilege to do this. Also, there are companies who help foot the bill. They pay the bills so that you can pay attention. That's all we ask. If you want to pay it forward, please share this with others, because Suncast was created to help illuminate the path for others that want to get into this industry. You want to learn how to build a business? Got over 750 episodes of people like Jim who have built these businesses and who have made this transition themselves. We are here for you. Our team is here for you. We'd love to help you share your story. If you know someone like Jim whose story deserves to be heard and they haven't yet been featured on Suncast, please reach out to us. team@suncast.me. We'll be happy to help share this with others. I can't do this without my wonderful team. So thank you to our amazing team. Jeremy Pingle, our operations manager, Chris Mottram, our amazing executive producer and editor, Herman Chalet, our production manager, and everyone else who would take it would take a tremendous amount of time to actually show gratitude for everyone who helps make this possible. You know who you are. The team at Suncast really does extend beyond just me. Might have started here as one person with an idea 9 years ago, but I'm thankful, as Jim expressed in this interview, and I want to express gratitude for those who help make this possible. And not the least of which is you. Thanks for tuning in. Remember, you are what you listen to. Thanks again for showing up, Solar Warrior. It's half the battle.